All right, task 4.1. Apply secure design principles in network architectures. And remember, if Larry doesn't go as deep, and there are 18 subtasks in this section here, you know what to do. Use the prompt at the end of the session and go deep as you need to. All right, this is a very important section. It actually spans all parts of the CISSP exam, as well as your real security posture having secure networks. There are 18 subtasks. So our first one, we're going to cover the OSI model and TCP/IP model and protocols. And if you can keep that in mind, and then everywhere else we kind of place them along that model, that'll probably be a good way to keep things framed up properly. All right, let's move on to these 18 subtasks. 4.1.1, OSI and TCP/IP models. These are the foundational models for understanding how data is transmitted across networks, and they are key to many topics on the CISSP exam. The OSI model, a newer model, has 7 layers. It comes from the TCP/IP model, a simpler model, which has 4 layers. For the exam, you need to understand the functions at each layer and how data flows from one layer to the next. For example, data moves from a user's application through the transport, where it gets a segment header, through the network, where it gets an IP header, and then over the data link, where it gets a frame header. The data link will then link it to some physical media. Knowing the OSI and TCP/IP models helps you understand which protocols and devices operate at which layers. For instance, IP operates at the network layer, while TCP works at the transport layer. Understanding these relationships will be crucial for many security questions on the exam. And if you're feeling that I didn't go deep enough for you, you know what to do. IP versions 4 and 6. These protocols are vital to communicating on the network, and understanding them is essential for your CISSP exam. So it'll test your knowledge on some of the differences between IPv4 and IPv6, especially when it comes to addressing and the size of the address space. So with the 32-bit address, IPv4 can only allow for about 4.3 billion addresses. There's 8 or so billion people, and with Internet of Things. So obviously we ran out in 2014. So with IPv6, 128 bits, we're not going to run out anytime soon. That's a long number. You can play with that. And IPv6 introduces a few other features, like the built-in support for something called a Anycast. They got rid of a broadcast, so everything is either broadcast or anycast. You will need to know the differences between this. And what I'm talking about is a unicast is a one-to-one. A broadcast is one to everybody. Multicast is when it's just, hey, select a group, all you OSPF routers. And anycast is if multiple systems are sharing an IP. So it's like, just give me the closest guy next to you. Whoever's got 2.1, whoever. Knowing the differences between them, and especially the address space, would be important on the exam. 4.3.1, secure protocols. Now in this context, they list IPsec, SSH, and SSL/TLS. These are vital for ensuring secure communications. They have encryption built in. They're network encryption protocols. These protocols encrypt data as they're being transported, so ensure that it's secure over transmission. So let's break it down. IPsec is a network layer protocol. It takes IP and secures IP. It provides encryption, integrity, and authentication, mutual authentication. We know both sides of the IP addresses. And it also provides something called replay protection. It's widely used for VPNs, especially like connecting site to site. It's also used for remote access VPNs, but depending on your needs, you might use another solution for remote access. Now, SSH and TLS operate at the transport layer. They can secure communications over any TCP connection and encrypt the data. TLS it was based on SSL, so sometimes people use them interchangeably. When they just say, SSL, well, today has been TLS, for the last 20 years. It's like they call cars running in horsepower. But TLS, very, very flexible. We mostly think of it as web servers, but we have a lot of things. Any TCP application can be secured over TLS, including our mail and some other FTPS if you need it. The exam will often ask about which protocols are more appropriate. So SSH can do whatever TLS can do, but it doesn't require PKI. And I'll let you imagine what could be done if I didn't require that. Quick hint, most botnets are run over SSH, but you're going to want to use SSH yourself for many, many things like remote administration to your devices. 4.1.4 Implications of multi-layer protocols. Some protocols do not fit neatly into one layer, and especially I like to think of ICMP, which is usually considered a network layer protocol, but it has a data field. So many people use it in ways it shouldn't be used. MPLS, multi-protocol label switching, also is associated with multiple layers. So what's important is how protocols can cross multiple layers interact with your security controls. Now this can enhance, but it could also create gaps if you're not paying attention. 4.1.5 Converged protocols. These are protocols that allow multiple types of network traffic, such as data, voice, and storage, to run over a single network infrastructure. This is an important concept for the exam because it highlights how modern networks need to support diverse types of communication while maintaining security. So let's look at some examples. CISSP allows SCSI commands to be sent over IP networks, enabling block-level storage devices across the same infrastructure to be used for regular network traffic. Voice over IP enables voice communication over IP networks, integrating telephony and data networks. Then there's InfiniBand over Ethernet, used for high throughput, low latency data transfers, primarily in data centers. The exam may ask you to consider the security implications of using converged protocols. For instance, combining storage, voice, and data traffic on the same network can increase the attack surface if not properly segmented or secured. Protocols like CISSP need encryption and authentication mechanisms to prevent unauthorized access to sensitive data. The integration of different traffic types makes security complex. But if you understand how to secure these protocols, which is key for passing the exam, then you're in good shape. Transport architecture. This is understanding how data moves across a network. For the exam, you may need to know about different topologies like the old bus, star, and mesh networks, as well as the management planes that control data flow. The data plane, the control plane, and the management plane. The data plane is responsible for forwarding data based on routing decisions. The control plane manages routing protocols, and the management plane handles the configuration and monitoring of networks. You'll also need to understand different switching technologies. The old cut-through, which begins to forward data before the entire packet is received. Today we're almost all store and forward, which waits for the entire frame, checking the CRC at the end, and then making the forwarding decision. These concepts are about optimizing network performance while ensuring security. Cut-through switching may reduce latency, but it can allow some types of errors or attacks to propagate. We don't support that anymore. For the exam, expect questions on when to use each topology or plane and how different switching techniques impact security and performance. 4.1.7 Performance metrics. This is essential for network efficiency and ensuring it meets both security and operational needs. The exam often includes questions about how these metrics impact both performance and security. So let's break them down. Bandwidth refers to the maximum rate of data transfer across a network. While high bandwidth is desirable, it doesn't guarantee efficient communication if latency and jitter aren't managed. Latency is the delay time between data transmission and reception. It's critical to understand for real-time applications like voice over IP or video conferencing, where even slight delays can cause issues. I like to think of bandwidth in the plumbing sense of how much water can I push through the pipe, and latency, how long from the time I turn on the faucet does the water come out. Jitter. Jitter is the variation in latency, which can be especially problematic for applications requiring a constant stream of data, like watching videos. Throughput is the actual amount of data successfully transmitted over a network and is typically less than your bandwidth due to network congestion and other errors of protocols overhead. Signal to noise ratio is particularly important on wireless communications as it measures signal strength relative to background noise. High signal to noise ratio means better data integrity and less packet loss. In the exam, expect to see questions where you need to analyze these metrics to optimize network performance while ensuring security. For example, high latency could lead to increased vulnerability in time-sensitive transactions, and low SNR could indicate a risk in a wireless network. 4.1.8 Traffic flows, north-south, east-west. And I warn you, these terminologies mean different things to different people. Traditionally, north-south refers to data moving in and out of data centers, typically between clients and servers. This is the traffic most people think of when they consider network communication, and it's often exposed to external threats, making it a priority for perimeter security like firewalls and intrusion detection systems. East-west is typically between systems within the same data center, such as server-to-server communication. Modern applications using microservices generally do a lot of east-west traffic between each other. Now, in software-defined networking, I have found that north-south has a different context. And so we have north between the controller talking to applications, and we also have southbound connections from the controllers to the devices. So be careful of the context and how the CISSP exam uses the term. 4.1.9 Physical segmentation. For example, in-band, out-of-band, and air-gapped. The CISSP exam may test your understanding of different segmentation methods and their security implications. In-band management means that you're managing network devices through the same network that carries the data traffic. This can simplify the infrastructure and also exposes management traffic to potential security risk, making it vulnerable to attacks if not properly secured. Out-of-band management involves using a dedicated network for management traffic. This approach enhances security as it keeps management traffic separate from the regular data network, and it ensures that devices can still be managed if the main network goes down. Air-gapped networks are completely isolated from external networks, providing maximum security for highly sensitive systems like those in military or other critical infrastructure environments. Air-gapping is an effective way to protect the critical systems, but it can make access, updates, and other maintenance a lot more cumbersome. The exam wants you to understand the trade-offs between these methods and why they're important. 4.1.10 Logical segmentation. This allows organizations to create isolated segments without needing physical separation. This is a key topic on the exam because it provides flexibility in securing different types of traffic across shared infrastructures. A VLAN, or virtual LAN, allows you to logically divide a network into separate segments, even if they're all running over the same physical infrastructure. This helps isolate network traffic and limits the spread of threats within the network, especially broadcast storms. Virtual private networks, VPNs, create secure, encrypted tunnels over public networks, enabling remote access and site-to-site communication while maintaining data confidentiality. Virtual routing and forwarding. This enables multiple instances of routing tables to coexist on a single router, allowing for traffic segmentation and network path isolation, even with overlapping IP addresses. Virtual domains can partition a single device, like a firewall, into multiple logical devices, each with its own security policies, providing a fine-grained control over network traffic. The exam will likely test your understanding of when and how to implement these logical segmentation techniques, depending on network requirements and security needs of the organization. For example, a question might ask something about sensitive traffic using VLANs or encrypted remote communications with VPNs. 4.1.11 Microsegmentation. It's a very cool, new, powerful method for isolating traffic at a very granular level, particularly in modern distributed network environments. For the exam, understanding the concept of microsegmentation and how it enhances security is critical. Network overlays and encapsulation create virtual networks on top of the physical infrastructure, allowing for flexible segmentation without changing the underlying network. This is especially useful in cloud environments. Distributed firewalls enforce security policies at the workload level, meaning each device or application has its own firewall rules. This reduces the risk of lateral movement of threats within a network. Intrusion detection and prevention systems. These can be integrated at microsegmentation level to detect and block malicious activity at a very granular level. And zero trust architecture ties into microsegmentation by applying the principle of never trust, always verify. Why not just trust but verify? Requiring authentication and authorization for every request, regardless of where it originates. The exam will likely include questions about microsegmentation and how it can improve security, particularly in cloud and virtualized environments. 4.1.12 Edge Networks. For the exam, you need to understand the role of edge networking, which is managing the flow of data in and out of an organization. So we need to understand the ingress and egress points, where data enters, ingress, or exits, egress is the network. These points are important for implementing security controls, such as firewalls and intrusion detection systems, to monitor and control traffic as it crosses network boundaries. Peering refers to the direct exchange of data between networks, typically between internet service providers or large content providers. While peering can reduce latency and improve performance, it also requires strict security measures to prevent unauthorized access or attacks on the network. Content delivery networks and edge computing are part of this conversation as they reduce latency by bringing data closer to the end user or processing it locally at the edge. For the exam, you'll likely encounter some questions about securing the ingress and egress points to prevent data leakages or unauthorized access. And you might be able to be asked to evaluate the security implications of peering arrangements and how to optimize edge security. 4.1.13 Wireless Networks. As wireless communication presents some unique challenges, you need to understand the different types of wireless technologies and their associated security concerns. So Wi-Fi 802.11 is the most common wireless technology used for local area networks. It provides high-speed internet access, but it's also vulnerable to some attacks like man-in-the-middle and other wireless Wi-Fi, WPA, maybe some old web attacks, if not properly secured. Bluetooth is a short-range wireless technology typically used for connecting devices like headsets and keyboards. This is obviously a wired one. While convenient, it is vulnerable to attacks like bluejacking and blue snarfing if security features such as pairing and encryption aren't enabled. Zigbee is a low-power, low-data rate wireless network standard used in home automation and a lot of IoT devices. Its power consumption makes it attractive for many IoT applications, but securing these devices is crucial to prevent them from being used and compromised and become vantage points or entry points into your network. Satellite communication provides global coverage for data and voice services, often used in remote areas or transportation sectors. Its broad coverage can expose communication channels to interception if not encrypted. 4.1.14 Cellular mobile networks, for example 4G and 5G networks. So it's very important that we understand these security challenges, particularly when it comes to authentication of both the user and is that really your cell tower or your provider. So 4G provides high-speed mobile broadband with improved security over earlier generations, but it's still vulnerable to attacks such as these stingrays that do man-in-the-middle attacks. They mimic legitimate cell towers and intercept mobile phone traffic to track users. Because of the security protocol for authentication, EAP, aka, was designed to authenticate the device, but not the cell tower itself. So this left it vulnerable to a rogue cell tower or a phony cell tower. 5G introduced new features such as lower latency, massive device connectivity, and network slicing. It was designed to mitigate some of the security issues found in 4G with support with the much stronger EAP TLS. TLS offers much stronger certificate-based mutual authentication. However, it hasn't been fully implemented and leaves 5G networks still mostly vulnerable to those stingray attacks. For the exam, it's important to understand how these vulnerabilities work and recognize that while 5G was designed to address these flaws, implementation shortcuts so far seem to have left it mostly open. 4.1.15 Content Distribution Networks. For the exam, understand how CDNs work and how they impact performance and security is essential. So they are distributed server networks. CDNs use geographically dispersed servers to cache and deliver content closer to users. This reduces latency and improves load times for users accessing large-scale applications such as streaming services or high-traffic websites. Load balancing. One of the key features of CDNs is their ability to distribute requests across multiple servers. This ensures high availability and prevents individual servers from becoming overwhelmed, which can enhance performance and reliability. Content optimization. CDNs often optimize content by compressing files, resizing images, and minimizing code. This improves content delivery speeds while reducing the bandwidth required for content delivery, contributing to much better performance. Distributed denial of service protection or mitigation. Many of them have built-in protection against DDoS attacks by absorbing and filtering malicious traffic. CDNs can help ensure that legitimate traffic can still reach its destination, preventing downtime and disruption. Analytics and insight. CDNs provide detailed insight into content delivery, performance, user behavior, and network activity. These analytics are important for optimizing your network delivery strategy and troubleshooting potential security or performance issues. For the exams, understand how CDNs improve security, especially in the context of availability and performance. 4.1.16 Software-Defined Networks. SDN plays a key role in modern networking by providing more flexibility and centralized control over network resources. It's a crucial topic for the exam, and let's go over some of the main concepts. Network programmability. SDN allows for centralized software-based control of the network, separating the control plane from the data plane. This enables administrators to program and manage network dynamically, adjusting the needs of the businesses without changing the underlying hardware. But it's not typically managers of humans. No, they're usually APIs. APIs are the critical component in software-defined networks as they provide the mechanisms to do the programming and make the changes. It makes it very easy to automate tasks like changing routing tables and security enforcement monitoring, but securing APIs is the challenge. It's probably the hardest step throughout my delivery of this entire 8 domains, so keep that in mind. SD-WAN uses as software-defined network principles to optimize WAN traffic, especially for organizations with multiple locations. Network functions virtualization. This allows for network functions such as firewalls and load balancers. Rather than relying on specialized hardware, these functions are deployed in the software, providing more scalability and reducing costs while still supporting critical security functions. And dynamic traffic management. This is where the APIs make it so dynamic, not an administrator, right? That's its greatest strength, the ability to dynamically manage traffic using APIs. In real time, it can do policy-based routing. But again, we need to secure those APIs. For the exam, it's essential to understand how SDN improves flexibility and scalability, and another reason why we need API security. 4.1.17 Virtual Private Cloud. This is a key concept for organizations leveraging cloud services while maintaining security and control over their network environment. Understanding VPCs is important for the exam, especially in the cloud security context. So in an isolated network environment, that means that you have an isolated section of the cloud where resources such as virtual machines and storage can be launched within a defined virtual network. This allows greater flexibility and control over cloud resources while still benefiting from the scalability and flexibility of the cloud. Customizable IP addressing. With VPC, you have full control over the IP address ranges, subnets, and network gateways. This level of customization helps mimic traditional on-premise networks while taking advantage of the cloud technologies, and allows you to maintain compatibility between the cloud and your on-premise systems, which enables some other security controls. VPCs come with a variety of built-in security mechanisms, such as security groups and network ACLs, due to these IPs, right, which control both inbound and outbound traffic at the instance and at the subnet level. Implementing these security controls ensures that resources within your VPC are protected from unauthorized access. And because you control the IP, you can have a nice hybrid cloud connectivity. The VPC can connect securely to on-premise data centers, allowing organizations to build hybrid cloud environments. It might be useful in cloud bursting in another domain. VPNs, or dedicated connections, are often used to ensure that the data flowing between the cloud and the on-prem environments remain the same, usually IPsec. Scalability and flexibility is one of the main advantages of a VPC. Its ability to easily scale resources up or down while maintaining network isolation. This scalability, which comes from the cloud, allows organizations to adjust resources based on demand, making VPCs a flexible solution for dynamic business needs. For the exam, you need to understand a little bit how VPC maintains isolation and security in the cloud environment. 4.1.18 Monitoring and Management. A vital area for the exam and for real world for sure. So a network observability goes beyond just basic monitoring, and it allows deep insights into the network behavior through looking at logs, metrics, and other traces. It helps administrators proactively identify potential issues before they become major problems, allowing for more effective troubleshooting and risk mitigation. Traffic flow analysis and shaping. We need to watch the patterns of traffic and probably for voice over IP, prioritize certain types of traffic. Capacity management. Ensuring that IT resources are properly sized to meet current and future needs is a focus of capacity management. It involves planning and allocating resources to avoid bottlenecks while balancing costs, making it a crucial part of both performance and security management. Fault detection and handling. Effective fault detection allows for quick identification and resolution of network issues, minimizing downtime and mitigating security vulnerabilities. Automated monitoring tools can alert administrators when performance drops or when unusual traffic patterns suggest an attack. Performance and risk monitoring. Continuously tracking key performance indicators, KPIs, such as latency and throughput, alongside key risk indicators like failed access attempts or unusual traffic spikes, helps ensure that the network operates securely and efficiently. Proactive monitoring allows teams to detect and respond to risks before they escalate into serious incidents. For the exam, you'll be expected to understand how these elements contribute to maintaining a secure and high-performance network. Whoo! We covered a lot of ground. I'm quickly summarizing. We covered very important understand OSI and TCP/IP models. We discussed how the exam will assess your understanding of these models as basic framework for network communication. You need to understand how data is encapsulated, data, segment, packet, frame, and the various protocols and devices associated with each layer. We talked about network segmentation, For the exam, it's essential to understand both physical and logical segmentation methods, such as VLANs, VPNs, and air-gapped networks. And we talked about some very important security protocols like IPsec, which secures layer 3 at IP. And then we talked about both SSH and SSL, now TLS, that do layer 4 traffic. And the difference being that SSH does not require a PKI CA signed certificate, right? So that's the big difference. Other than that, they work basically the same. All right, let's go into our test your knowledge slide coming up next. And here it is. Yeah, the exciting part. I hope you're having fun with this. I want to hear from everybody. So again, if you see the underline, like under the 10 question, of course, feel free to tweak it. Tweak anything. I encourage you to play around with this. You just go back to the PDF and cut and paste it again anyway. But for studying the topics again on line 5 or the option 5, change that thing to any domain, task, subtask, or concept you need to go a little deeper on. See you soon.